and welcome back to AGT-STEM. Today we're going to be watching a video on plutonium. So, without further ado, let's hop to it. Whoopsie daisy.
Okay, so I'm going to talk to you now about plutonium.
So I once referred to uranium as the boogeyman of the periodic table, but if uranium is a boogeyman, then there is a Hannibal Lecter of the periodic table, and it's a couple of places to the right, and that element is plutonium.
Plutonium has a really quite nasty reputation. For example, there's a book here, Plutonium, History of the World's Most Dangerous Element.
When the human race evolved, it evolved with uranium in the environment, so we physiologically can actually deal with it to some extent. Plutonium is a man-made element. It wasn't there in the environment when we evolved, and this means we've got essentially zero tolerance to it, so that makes it quite dangerous for us.
We're at Sellafield in the northwest of England. We're at the NNL Central Laboratory. We're interested in plutonium because we need to be able to recover it from spent irradiated nuclear fuel.
You can't just use plutonium in a regular laboratory. You have to have a laboratory which is specifically designed to handle it, so it's handled safely.
It's at the point in the periodic table where it does interesting things.
There are not many elements which you can say when they were created. You can sometimes say
It's kind of weird because it seems weird to say like the element was created rather than it was discovered, because normally they're not made, they were just found.
it was discovered in 1869 or 19 whatever, but plutonium was made for the first time in 1940. The reason that it was made is that it's a radioactive element and it decays away with a half-life that depends on which particular isotope it is. If plutonium was created at some time during the formation of the solar system, it has all decayed away long before scientists ever started looking for it on Earth.
I have seen a lump of plutonium once. I don't think I could tell you where I actually saw it, but it does just look like a shiny piece of metal. What we'll see today is plutonium in solution. And that's really interesting because plutonium's got some really intense colours, and the colours change depending on the oxidation state of the plutonium as well. It's incredibly dense as a metal. You could take to it with a hacksaw and the hacksaw blade would break before you chipped any plutonium off. The sheer density is shown by the fact that a golf ball sized lump of plutonium would be over 1 kilogram easily, really quite heavy stuff.
So here the intention is to recover the plutonium from spent nuclear fuel. Plutonium is present in about 1%. What we do is use solvent extraction in order to remove the plutonium from the fission products in the aqueous phase and move the plutonium up into a solvent phase. And that solvent phase is a mixture of tributyl phosphate and a diluent called odorless kerosene. Here we have some plutonium nitrate, and this plutonium is in oxidation state 4, and that's the oxidation state that's extractable into tributyl phosphate. I've got two separate solutions here. They're both plutonium nitrate, they're just at different concentrations.
It is dangerous for several different reasons. It is dangerous because it is the basis of atomic bombs. The second atomic bomb, so-called Fat Man, that was dropped on Nagasaki in 1945, contained plutonium, and it was the plutonium that made it explode. It was a bigger bomb in terms of the size of explosion than the first bomb that was dropped on Hiroshima. But it's also dangerous, plutonium, because it is very poisonous. Many heavy metals are poisonous, particularly, say, thallium. But plutonium is poisonous not just because of its chemistry, but because of its radioactivity. Plutonium decays radioactively by emitting alpha particles, helium nucleus. And when that hits the cells of your body, it can cause terrific damage and that can lead to cancer and so on.
I'm going to take some 30% TBP. So this is the solvent phase. You can see there it hasn't been mixed yet. The solvent is less dense than the aqueous phase and resides on top of the aqueous. But you'll see in a minute that that brown colour will go up into the top phase.
According to this book, there is a club, or there was a club, in Los Alamos, the bomb factory, where they developed the chemistry of plutonium and made the plutonium bomb, of 4 people, which had rather a strange name. This says UPPU, which means your urine contains plutonium. And these are people who, through some sort of accident, had plutonium in their body. There was one person that was described called Margall, who was working with a glove box, just like the ones that we saw in the NNL labs. And he had, for some reason, a needle, and he stuck the needle through the finger of one of his gloves. And he pulled out his hand and saw that there was a tiny black speck in his hand, which was a fragment of plutonium. And although the doctors try to dig this out, for the next 50 years, plutonium could be detected in his urine. I mean, it wasn't very high concentration. According to this, he had to provide a gallon of urine, that's 4 litres, before they could detect the plutonium, but nevertheless, he survived.
Okay, so I've got 2 samples there with plutonium nitrate at the bottom and tributyl phosphate odorless kerosene on the top. So what I'm going to do now is put them into this device, which is called a vortex mixer. So while that's mixing, plutonium's going up into the solvent phase. It'll form an emulsion, and the solvent will then start to disengage from the aqueous phase, and the 2 phases will separate out.
Plutonium is formed in the nuclear fuel of nuclear reactors. Uranium, which has atomic number 92, can be transformed into plutonium, which has atomic number 94, by absorption of neutrons. So the uranium absorbs neutrons. That is the uranium-238, the sort of uranium that does not spontaneously fission and provide the energy for the nuclear reactor.
The Hanford, Washington Active Material Production Plant, where uranium-238, the most abundant isotope in natural uranium, is converted into a completely new fissionable element known as plutonium-239.
So it's the so-called, if you like, inactive uranium isotope, but that can absorb neutrons and be transformed into plutonium.
Okay, that should be done now. Looks like an emulsion at the moment. As it separates, you'll see that the top phase has now got the colour in it. The plutonium nitrate has now formed a chemical complex with TBP molecules, and those TBP molecules have made the plutonium soluble in the organic phase. In the reprocessing of irradiated nuclear fuel, all the fission products would now be in this bottom phase, and the plutonium and uranium would be in this top phase here.
That's cool. It's kind of great. It's kind of weird how it just like switches. Like one is here and then the other's up here, and then they just swap. You shake it and it swaps. That's weird.
So you've separated them out.
Plutonium itself, the metal, is actually a very fascinating material. I've never seen it, but it's meant to be a very hard metal, but it has a surprisingly large number of allotropes. An allotrope is a different crystal structure. Plutonium has 6 or perhaps 7 different allotropes, which differ in their hardness, their mechanical properties, even their density. This makes the machining of plutonium, which is necessary for manufacture of nuclear bombs, extremely difficult. It also has quite a low melting point. It melts at 639 degrees centigrade, which is really very low melting point for a heavy metal. For example, osmium, which is not far away in the periodic table, has a melting point well above 3000 degrees centigrade. Some of the isotopes of plutonium are so radioactive that they're really quite hot. So if you feel the sample, some of them can even be glowing red hot, but even the less radioactive ones apparently feel quite warm to touch, though you have to be quite brave to touch them.
What happens in a solvent extraction process is that the solvent is separated from the aqueous phase, and then new aqueous liquor is added to that solvent to try and recover the plutonium from it. What we're going to do is remove the aqueous liquor from this now, from the bottom, and replace it with some fresh liquor that's got a chemical within it that will promote recovery of the plutonium from the solvent. I'm taking the aqueous phase out from the bottom. Of course, on an industrial scale, this is done with a variety of devices.
Why are you trying to get the plutonium on its own? Because it has to be disposed of in a special way, or because you want to reuse it?
It's separated and into a pure form so that it can be reused in things like MOX fuel, which stands for mixed oxide fuels. So that's where you combine plutonium with uranium and you can put it back into nuclear reactors and generate new energy.
There is also an interesting feature that when they decay radioactively, they give off these nuclei of helium atoms. So as you get an older and older sample of plutonium, the helium builds up in this crystal structure. So although it looks like a piece of metal, in fact it has helium atoms inside it, rather like the fruit inside the cake. And because of this crystal structure, you tend to have crystallites with boundaries, so-called grain boundaries between the crystallites, and the helium can accumulate on the grain boundaries and weaken the metal quite substantially. The helium has two problems. Obviously, in the short term, if you are somebody who makes bombs, you have to be careful that you don't build up too much helium in the core of your bomb, because it then may not perform properly.
Here in sequence are the 4 snapper blasts, detonated atop their steel towers on the 7th and 25th of May and the 1st and 5th of June.
The second problem is that if you are storing plutonium, which has come from reprocessed nuclear fuel and is just being stored at waste until it's safe to be in the environment, you will bury it somewhere in the ground in a very strong container. And when you're designing that container, you have to allow for the fact that your metal will start producing a gas as it decays, and therefore your container has to be able to withstand the internal pressure so it doesn't suddenly explode, which would be embarrassing, if not for you, for your grandchildren or their grandchildren when they suddenly discover that these secure containers have blown up.
Did you just describe the explosion of a container containing radioactive plutonium waste as embarrassing?
Yes.
I'll tell you what, like, for all the excitement about plutonium,
It would be pretty embarrassing if you had locked away your plutonium waste and then, like, decades later, kaboom. That would be quite embarrassing.
it all looks pretty harmless there, that muddy brown solution.
Well, it's highly radiotoxic, and you wouldn't want to drink that either.
Well, I won't then, even though it looks a little bit like Coke.
In order to get that plutonium back into the aqueous phase, I'm going to use 2 different techniques. One is a reduction to get plutonium-4 into a plutonium-3 oxidation state. So what I'm going to do to this one is add a chemical called hydroxylamine nitrate. This is another method. We're using a complexant, which means that it forms a chemical molecular compound, and the chemical that we're using is called acetohydroxamic acid. When we've mixed it, all the plutonium will be in the bottom. Okay, so this is the acetohydroxamic acid solution, and it's just disengaging now between the aqueous and the organic phase. And as you can see, the colour in the top phase is completely gone now. So that's the solvent. Solvent is now...
That's crazy. That's like super cool. Science is almost like magic. Except magic is fake and this is real.
free of plutonium, and it's come back into the aqueous phase. And that aqueous phase can then be sent to downstream plants for final purification and conversion into the final form, which is plutonium dioxide. So this hasn't been quite as effective, but you can see there the orange colour that was in the top half has been diluted now, and most of the plutonium is in the bottom half as plutonium-3.
So I have another story. I've told it before, but it's really good, and Brady wants to hear it again. One of the people who taught me chemistry, a professor at Cambridge, Alfie Maddock, worked on plutonium during the Second World War. And one night, when he was really quite tired, he spilt the entire United Kingdom supply of plutonium, which was 10 milligrams, onto the table, the bench that he was working on. He was really upset. He'd lost the whole country's supply. So he got a saw and cut a hole in the top of the table. He burnt the wood, and from the ashes of the wood, he got back 9.5 milligrams of the 10 milligrams he'd lost. And he would have hidden the whole thing, but he was so tired by then that he didn't have the energy to repair the tabletop. So when people came in the next morning, there was a big hole, and so they discovered what's happened.
So the one on the left here with the red solution is plutonium-4 with acetohydroxamic acid. On the right here, it's plutonium. The blue plutonium at the bottom is plutonium-3 that's been reduced by hydroxylamine nitrate.
Well, that was cool. Also, if something goes wrong, I don't think that cutting a giant hole out of your table is the best solution, especially if you're not going to cover that up in any way. So don't cut a hole in your table, and be careful when using plutonium. Actually, just don't use plutonium unless you're like a professional scientist. I don't want anybody killing anybody over here. Thank you so much for watching, and we'll see you next time. Stay smart. Bye!